Have you ever pondered what the universe's first moments of structure were like? Quite a thought, isn't it? Let's go back, way back, to the time just after the Big Bang. Picture a hot, dense state of existence, filled with energy, matter, and potential. This was the beginning, the birth of our universe about 13.8 billion years ago. Now, what's fascinating about this period is not just the Big Bang itself, but what happened immediately afterward. The universe began to expand, but this wasn't a chaotic, uncontrolled expansion. No, it was nearly perfectly balanced by gravitation. A delicate dance between the forces of push and pull, expansion and gravitation, set the stage for the emergence of structure in our universe. But it gets even more interesting. Our universe wasn't born perfectly smooth. It had imperfections, little inconsistencies in its density and temperature. You might think, well, that doesn't sound ideal, but these imperfections were crucial. They created variations in the gravitational field, leading to the formation of complex structures. We're talking about the birth of stars, galaxies, and eventually solar systems like our own. These imperfections and the balance between expansion and gravitation shaped the evolution of our universe. They were the architects of the cosmic structures we see today when we look up at the night sky. And the most incredible part, if these early imperfections hadn't existed, if the balance between expansion and gravitation had been slightly different, our universe would look significantly different, perhaps even unrecognizable. So the next time you gaze at the stars, remember the universe's first moments of structure. Remember the delicate balance and the essential imperfections. They are the reason we can marvel at the cosmos today. Without these early imperfections and balance, our universe would look significantly different, perhaps even unrecognizable. Imagine a tightrope walker maintaining a careful balance to prevent a disastrous fall. That's a bit like our universe in its infancy. In those early days, the universe was a dancer on a wire, delicately poised between expansion and gravitation, and it had to maintain this balance for a staggering 6 billion years. Now, let's delve a bit deeper into this cosmic ballet. The universe, in its first moments, was expanding at a rapid rate, but at the same time, the force of gravitation was pulling everything back in. These two forces were in a tug of war, but they were evenly matched. This perfect balance was the universe's tightrope. This balancing act was crucial for the formation of complex structures. It was like the universe was setting the stage, preparing the conditions for the birth of stars, galaxies, and eventually life itself. The universe, in its careful dance, was creating the building blocks of everything we see today. But what if the universe had been a clumsy dancer? What if the balance between expansion and gravitation had been slightly off? Well, we might be living in a vastly different universe. If the universe had expanded too quickly, dark energy would have been undetectable, and the universe would have evolved differently. If gravitation had been too strong, the universe might have collapsed back in on itself. So the universe's tightrope act was a matter of life and death. If the balance had been tipped, if the universe had fallen off the tightrope, we might not be here to talk about it. The universe had to maintain that perfect balance to allow for the possibility of life. A universe tilted too far, one way or the other, might not have been capable of supporting life as we know it. So next time you look up at the stars, remember the universe's delicate dance. Remember the tightrope walker, maintaining that perfect balance, and be thankful for the universe's sure footing, for without it, we wouldn't be here to marvel at its wonders. We live in a universe that, against all odds, is perfectly flat. But what does that mean? Well, let's take a moment to ponder this. When we talk about the universe being flat, we are not referring to a two-dimensional plane. Instead, it's a way of describing how space is shaped on a cosmological scale. Imagine you're an ant crawling around on a balloon. To you, the balloon's surface might seem flat, but pull back and it becomes clear that the balloon is round. Now suppose you're an ant in the universe. To you, the universe seems flat because you're so small compared to the size of the universe. But what shape is the universe really? To answer that, we have to look back to the early moments of the universe's life, to a time when the initial expansion rate and the total energy density of the universe were perfectly balanced. This balance left no room for spatial curvature, The result? A universe that, on a large scale, is flat. This flatness isn't just a cool cosmic quirk. It has profound implications for the universe's structure and evolution. A flat universe means that the geometry of space isn't warped by the presence of matter and energy. Straight lines stay straight, and parallel lines never meet. This allows for the formation of complex structures we see today: galaxies, star systems, and even life itself. But what if the universe wasn't flat? If the balance were slightly skewed, we'd be living in a curved universe. This would warp the fabric of space and time, bending straight lines and causing parallel lines to meet. The universe's structure would be vastly different, and life as we know it might not exist. So when we marvel at the grandeur of the cosmos, let's also take a moment to appreciate its flatness. This seemingly minor detail has shaped the universe's evolution and made our existence possible. Our universe, it seems, hit the jackpot when it comes to its shape. In a world where matter and antimatter should exist in equal parts, why is there more matter? This is the question that's been puzzling physicists for decades, and it's a key piece of the universal jigsaw puzzle. You see, according to the standard model of particle physics, for every particle of matter created in the Big Bang, an antiparticle, its mirror image with opposite charge, should also have been formed. So, in a perfect world, or rather a perfect universe, matter and antimatter should have annihilated each other upon contact, leaving behind nothing but energy. But that's not what we see around us, is it? We exist, the stars, galaxies, and cosmic dust exist, all made of matter. So, where's all the antimatter? The answer to this conundrum, my friends, is one of the greatest unsolved mysteries in physics. This puzzle, known as the matter-antimatter asymmetry problem, has left scientists scratching their heads. Some theories suggest that in the universe's infancy, certain conditions led to a slight overproduction of matter particles over antimatter. But what were these conditions and why did they favor matter? That's the million-dollar question. This asymmetry, this slight favoritism towards matter, might have had a profound impact on the early structure of the universe. If there were equal parts of matter and antimatter, they would have annihilated each other, leaving behind an energy-filled but structureless universe. But because there was more matter, it survived the annihilation and went on to form the stars, galaxies, and other cosmic structures we see today. This slight imbalance in the cosmic scales, this tiny deviation from perfection, led to the rich and complex universe we call home. So the next time you gaze up at the night sky, remember that each star, each galaxy, is a testament to the universe's greatest unsolved puzzle, the matter-antimatter asymmetry. It's a subtle reminder that sometimes it's the imperfections, the asymmetries, that lead to the most beautiful outcomes. The universe keeps its secrets well, doesn't it? So we've journeyed through the universe's first moments of structure, but what have we learned? Quite a bit, actually. We've learned that our universe, born from the hot Big Bang around 13.8 billion years ago, found its balance between expansion and gravitation in nearly perfect harmony. This equilibrium allowed for the formation of complex structures, the building blocks of our stars and galaxies. We've also discovered the significance of imperfections in the early universe. Had the universe been born perfectly smooth, there would have been no structure, no fascinating chemical reactions. The imperfections provided the necessary sparks for the universe to evolve and create the structures we see today. Our journey also led us to the concept of a flat universe. The initial expansion rate and the total energy density of the universe were perfectly balanced, leaving no room for spatial curvature. This resulted in a universe that is, for all intents and purposes, flat. Lastly, we grappled with the enigma that is the matter-antimatter puzzle. The presence of more matter than antimatter in the universe is a conundrum that remains unsolved, but one that continues to fuel curiosity and scientific exploration. Each of these factors, from the early balance between expansion and gravitation to the significance of imperfections, the flatness of the universe, and the matter-antimatter puzzle, have played crucial roles in shaping the universe's structure and evolution. They've guided us from the universe's first moments of structure to the present day and will continue to influence its future trajectory. Remember, each star in the night sky is a testament to the universe's early moments of structure. So the next time you look up, take a moment to appreciate the cosmic ballet that brought us here. Please like, comment, and share this video if you've enjoyed our journey through the cosmos together.